This video is the second part of section 11.2. We're dealing with tests for independence using chi-squared. We will be again using two-way tables for this test. All right, so in this one, we're specifically talking about tests for independence, and we'll be then getting our appropriate chi-squared statistic calculations. We'll do the same calculations will look a lot like we did for homogeneity up above here in the previous part of this section. It really boils down to the difference between these two tests really boils down to how we got the data. So we will again, with this test, we will be looking at the relationship between categorical variables. We will look at one population and we will take one sample from that one population, and then we'll break the data up based on two categorical variables. The null hypothesis, a lot like the test for homogeneity, but the way we say the null hypothesis here is that there is no association. The alternative will say something very similar to the null, except it'll be that there is an association. All right, so the chi-squared test for independence, right? So to differentiate that between the test for independence and the test for homogeneity, the test for independence actually has just one sample from one population. So the test for homogeneity, we have two different samples from two different populations based on some criteria, like maybe we did a sample of males and a sample of females for homogeneity, two different samples. For independence, we would just take one sample, and then after we take that one sample, we would break the data up based on maybe gender. So very sort of nuanced difference between these two tests, and it all boils down to how many samples you had. Test for independence, you'll have one sample. Test for homogeneity, you can have two or more. So for example, if you remember homogeneity, the restaurant example we did, we had three different treatments actually, so we weren't sampling in that case, but we had three different treatments, each from a different type of music playing on a particular night at the restaurant. All right, so the conditions we're going to look at are very similar, regardless of whether you're doing a test for independence or test for homogeneity. We still have the expected counts will all need to be greater than 5. The randomness and 10% also apply as needed, just like for homogeneity. All right, so here are the null hypothesis and alternative hypotheses. The null is going to say that there is no association between the two categorical variables, so depending on what they are. Remember, now we're talking about population. We're not really referring directly to the data we collected when we're dealing with null and alternative hypothesis. The alternative hypothesis will say that there is an association. Or the chi-squared statistic is calculated the exact same way. We have a two-way table. We'll have to do this sum over every cell in the two-way table. The degrees of freedom also calculated the same way for homogeneity and for independence. And as well as the p-value. The p-value is just the area under the chi-squared curve to the right of the critical value that we found. All right, so let's look at an example. Are men and women equally likely to suffer lingering fears from watching scary movies as children? Researchers asked a random sample of 117 college students to write a narrative account of their exposure to scary movies before the age of 13. More than 1/4 of the students said that some of the fright symptoms are still present when they are awake. The following table breaks down these results by gender. So we took one sample and then collected the data and then broke it down based on gender and whether or not they still have fright symptoms, yes or no. All right, so this is a Minitab printout of the example we were just talking about in the last slide. I'd like you to calculate your expected values. Pause the video, calculate those, and then restart the video and I'll reveal the answer. Okay, so if you remember, you take the row total 36 for the first one here. You take your row total 36 times your column total of 38 and divide that by your table total of 117. So do that for each of those. That's how you calculate those expected values. Now calculate your chi-squared contribution using our chi-squared statistic formula. Again, pause the video. Okay, so we get these values here. Remember, that's the expected minus the observed minus expected quantity squared over the expected, and then you would add all of those up to get your chi-squared. Of course, the Minitab printout already has the chi-squared on the bottom. That difference is really just round off error, not a crucial issue there. All right, and they also gave us the p-value of 0.045. Ultimately, we would use our calculators probably to calculate that, or use your chi-squared distribution table to calculate that. All right, so explain why this is a chi-square test for independence and not a chi-square test for homogeneity. Basically, it boils down to the fact that we are using one random sample from one population, and after we collect that data, we then break it up based on gender. All right, state an appropriate pair of hypotheses for this particular same example. I'll pause the video, write those out, and then I will reveal once you start up the video again. Okay, so the null hypothesis always has that no association, and so we're here in this case we say there is no association between gender and the ongoing fright symptoms in the population of college students from where we sampled. The alternative would just be the exact same thing, except it will say that there is an association. All right, so where do we see the largest contribution to the chi-squared statistic? Now, normally we don't even ask this question until we do a four-step process and we reject the null hypothesis. If we don't reject the null hypothesis, we typically don't bother doing this. They're sort of asking this question in reverse order this time. So figure this out, pause the video, figure this out, and then I'll reveal once you start it back up. Okay, so clearly this is where our largest contribution is coming from. This is men who admit to having fright symptoms. We would expect many more of them than, we expected almost 12 of them to say they still had symptoms, but only 7 did. So not only do we want to say where the largest contribution is, we kind of want to say, like, well, are there more than expected or less than expected? All right, so we want you to interpret the p-value. Again, they gave us the p-value down here in our Minitab printout. If they hadn't, then we would have had to take our chi-squared statistic and use our calculator or our chi-squared table to calculate our p-value. All right, so interpret the p-value in context and then come up with a conclusion based on an alpha level of 0.05. Again, pause the video. All right, so remember the p-value always says, essentially if the null hypothesis is true, this is the probability that we would get values as extreme or more extreme than the one we got. So if gender and ongoing fright symptoms really are independent of each other, in other words, that the null hypothesis is true, in this population, then there is a 0.045% chance or 4.5% chance of obtaining a random sample of 117 students that give a chi-squared statistic as large as the one we got or larger just by chance alone. All right, and so what would be our conclusion with an alpha level of 0.05, 0.01? Because our p-value is greater than our alpha of 0.01, we would fail to reject the null hypothesis. We do not have convincing evidence that there is an association between gender and fright symptoms in this population of college students. All right, so this is an example of chi-squared tests for independence. We looked at one sample of 452 high school students. So this is why it's independence, because it's exactly one sample. And then after we took the data and we broke it up on whether the person answering the question was a male or a female, and then also we broke it up on which of their fingers was longer, either their index finger or their ring finger, or were they the same length. All right, and so they're asking us if this is an observational study or an experiment. Clearly, we cannot assign a treatment here. The treatment would be what gender you are. So that's clearly going to be an observational study. All right, so the first thing we want to do is fill out this Minitab table. I purposely left off the information on the last bottom two cells. So come up with the expected value and the contribution for females and males having an index finger and ring finger the same length. Pause the video, and then once you start it up again, I'll reveal the answer. Okay, so we get our expected values and our chi-squared contributions. All right, and now let's do a four-step process. So do the data provide convincing evidence of an association between gender and relative finger length for high school students who filled out this survey? Okay, so state, you come up with your alpha level, and you will probably use 0.05 because they don't tell us. And then come up with your two hypotheses. Pause the video, write it out, and then check it by starting up your video again. Okay, so we're using an alpha level of 0.05. The null hypothesis is that there is no association between gender and relative finger length in the population of U.S. high school students who filled out this survey form. Okay. The alternative is going to be that there is an association between gender and relative finger length. Okay, so the plan. Remember, we want to write what our inference procedure is and check our three conditions. So pause this video, write those out, and then start it up when you're done. All right, so this is a chi-squared test for independence. Clearly, we said this before. It's independence because there's only one sample. The sample was randomly selected. We can assume that there are more than 4,520 high school students in the U.S. that filled out this survey. And then the large counts, you can look at them in the table up above. All the red numbers are at least 5. Okay, so come up with your chi-squared statistic, come up with your p-value, draw a curve, everything that we're supposed to do in our do. So pause the video again. Okay, so I showed a little bit of the calculation that you would do for the chi-squared. That's always helpful for people who are grading your test. But then also, ultimately, you would just add up all of the third numbers of each of the cells. It comes up to be about 29. All right, so if we're going to use our table C, then we need to know the number of rows minus 1 times the number of columns minus 1. So that's 2 degrees of freedom. The best thing we can come up with from our chi-squared table is that our p-value will be less than 0.005 because that's the smallest value on the row 2 degrees of freedom on that table. We can use our chi-squared CDF in our calculators. The lower value is our statistic, upper value of 1,000, and degrees of freedom of 2. And that gives us 0.0000005, or you might say approximately 0. All right, so pause the video, write the conclusion, and then start up the video again. Okay, so our conclusion has the same format as almost every other hypothesis test conclusion. Our p-value of approximately 0 is less than our alpha of 0.05, so therefore we're going to reject the null hypothesis. We have convincing evidence that there is an association between gender and relative finger length in the population of U.S. high school students who filled out this survey. Okay, so here is your homework, and just as a warning, number 45 is a 4-step problem. Please make sure that you're using the proper 4-step procedure. Labeling the 4 steps is good, but also making sure that you do all the things inside each of those steps that's required.